So I'm going to try this one more time. Sorry for the interruptions. Apparently there are not other classrooms at this time of day or any time that's during business hours when the building's actually open. But anyway, we're just working through the example with the patients with gestational diabetes. We're trying to find the adjusted standard deviation so we can go through and finish out the rest of our calculations. So if we're adjusting the standard deviation based on the information that we're given, we're just going to take sigma over root n. So same idea, we're just taking sigma over root n. Okay, and here I know that sigma is given as 10, and I just have root n as root of 1, which is 10. Which that kind of makes sense if we're only pulling one sample. Of course, it's not really going to change the standard deviation or the mean for that matter. Well, we'll look at this first. But anyway, that's not going to change the standard deviation if we're only pulling one sample. It's not making it smaller, really not that great of a sample size, but it doesn't mean that we can't go through the calculations. So next we're going to follow through exactly what we did in chapter 11. So say third, we're going to calculate the z-score. Okay, so now to do that we have z equals, okay, this time we're going to use x bar, so 140, because that's what we're trying to make a prediction about in terms of the population, minus the mean, 125, divided by our adjusted standard deviation, which is technically 10 over root 1. Right, so if you do the calculator work there, which I believe I have, you should get 1.5. So this would equal to 1.5. And just real quick, I have to work my drawings off here. So of course, 140 is greater than 125, so we want that over here. There we go. Okay, so we're looking for that little shape piece there. All right, so now I've calculated the z-score. From here, I'm just going to use the same process that I did in the chapter 11 video. So I need to look up that z-score. I need to look it up. Right, when I do so, I'm just going to go down to 1.5, so down to 1.5. And then I see that I get 0.4332. So I know that the probability that goes with that is 0.4332. Okay, so now remember, from chapter 11, really what this represents is the distance, the probability of that sector, that piece in between 125 and 140. So I know that 432 is really just, 0.4332 is really that piece. Therefore, to find my entire probability, this shaded chunk right here, I need to subtract that from 0.5. Okay, so now what I would get is the probability that x bar is greater than 140 is equivalent to 0.5 minus 0.4332, which is really just equal to 0.0668. Okay, so on this we can see that since we only pulled a sample of 1, it didn't change our standard deviation. So this really looks a lot like chapter 11, except for we have the root 1 down there. All right, but of course we want to see more examples of this, so I'll do another basic one like this with a small sample of 1, and then we'll see how if we take a bigger sample, it actually changes our results. So let's go ahead and look at another example. This one, another medical example. It says hypokalemia is diagnosed when blood potassium levels are low, below 3.5 MEQs per deciliter. Let's assume that we know a patient whose measured potassium levels vary daily according to a mean, so that's a population mean, that's basically the mean of her blood level, of 3.8 and a standard deviation of 0.2. If only one blood measurement is made, what is the probability the patient is misdiagnosed as hypokalemic? Okay, so with this, we know that we have population mean, population standard deviation, and that we're making predictions about this one patient. So we're really trying to make a prediction about the sample mean. This time we're just taking one of her samples, one sample of her blood, and finding the levels for it. So on this, we know that she'll be misdiagnosed as hypokalemic if the levels are low, so below 3.5 MEQs per deciliter. So this time what we're looking for is the probability that x bar is less than 3.5. So I'm going to draw a little picture here. We know our mean, the mean of this level in our blood is 3.8. Okay, 3.5 is below that, and we're finding the probability of being less than that. Okay, so we're looking at 3.5 or lower here. Okay, so the next thing that we need to do, since we have pulled the sample, this one blood measurement, is adjust our standard deviation, even though computationally it's actually going to look the same. But either way, we need to adjust the standard deviation. Okay, so to do that, I have sigma over root n equaling to 0.2 over the square root of 1, which is of course just 0.2. Okay, now, similar to what I've done before, so to find the z-score. So I have z equals, okay, 3.5 is what I'm treating as my data value now, even though it is the sample mean, minus 3.8. Okay, over, and then I'm going to use my adjusted standard deviation, which is 0.2 over root 1. If you wish, you could just put 0.2 in there as well. All right, so if I finish out this calculation, I see that I get a negative 1.5. So if I pop that in my calculator, I get a negative 1.5. Right, we still need to look this up. Okay, and remember from the video from chapter 11, if I use the table that I typically use, the bell curve is perfectly symmetrical, so I can just look up positive 1.5 and it holds the same value as negative 1.5, and that would be 0.4332. Okay, so I looked it up, we got 0.4332. Okay, I know that that goes with that blank space in between 3.8 and 3.5, so I know this part is 0.4332. Okay. And now to find my final probability, so the little pencil part right here, I'm just going to take this half of the bell curve, so this 0.5 probability, and subtract the 0.4332. So what I'm left with is the probability that x bar is less than 3.5 is equivalent to 0.5 minus 0.4332. And if you do that calculation, you get 0.0668. Okay, so this means that the probability of misdiagnosing is 0.0668. Okay, so thinking about this, remember, we have this patient's blood levels on average, so we know that she's not hypokalemic, but the probability of this happening, of misdiagnosing, if we just take one measure, is still there. So if we just pull out one measure, don't consider the entire amount of her blood, which we wouldn't usually anyways, then we know that we could potentially misdiagnose her. Okay, so now we're going to do another piece with the same kind of wording example, but I'm going to take more samples. So we're going to see what happens when we pull more samples. Theoretically, what's going to happen is our standard deviation is going to get smaller, and we'll actually see that this probability changes as well. If you thought about it intuitively, you would guess that that probability, this one, is probably going to get even smaller. So the bigger sample size we take, the more accurate it becomes, and the less likely it's going to be to misdiagnose this patient. All right, so let's stem off this and try another part. Okay, so this time, let's see what happens if we take 4 measurements. So how about if we take 4 measurements? Okay, so here my n is going to be 4. Right, draw my picture, that's going to look exactly the same. So we still have the 3.8 and the 3.5, and we're looking for the probability of being less than that. Okay, so you should see we do need to adjust the standard deviation, and that's because we have population information that we're given up here, and we're pulling a sample of 4 and making predictions about the sample mean of this sample, so the average level of, potassium in this person's blood from or based on the sample. Okay, so we have sigma over root n. I know sigma was given as 0.2, and I'm dividing that by the square root of 4. If you do the calculator work there, I guess I didn't do it, but you can pop that in the calculator if you want to. Okay, so either way, we've adjusted the standard deviation, and now I want to carry through my z-score calculations just like I did before. So I have z equals 3.5 minus 3.8 divided by my adjusted standard deviation, so 0.2 over root 4. Right, if you go through and pop that into your calculator, you should get -3. Right, so now I need to look that up. And again, I can use the table that I usually use, even though you can pick which ones you prefer. So I'm going to go down to 3.0, since I know that that's symmetrical to negative, so it doesn't matter which one I look up. And I get 0.4987. So now I know the probability that goes there is 0.4987. Okay, so what this tells me is when I'm in between 3.8 and 3.5, if my z-score is -3, this little probability is 0.4987. Okay, I know that I want this shaded region right here. So this guy here is 0.5 because it's half of the bell curve. And to get that final probability, I have the probability that x bar is less than 3.5 is equal to 0.4, long day, sorry. Okay, so 0.5, this green half right here, minus my red, the blank spot right here, which is 0.4987. Okay, and that's going to give me 0.0013. Okay, so what this tells us is the probability of misdiagnosing is 0.0013. Right, so now that I've pulled a bigger sample size, I'm not only looking at one sample of this person's blood, I'm looking at 4. I know that the likelihood of me misdiagnosing is even less, therefore that actually made my measurements even more accurate, which kind of makes sense if you just think logically. Let's say we ask a survey question, and on that question we ask everybody, oh, do you love math? Well, if everybody is only 2 people and say they're both math professors, well, they're probably both going to say right. I would think that we would all not consider that very accurate. However, if we say expand that survey to 1,000 people and then vary who we ask, that would be a lot more accurate because you're getting a bunch of different viewpoints. So it's the same kind of idea. The more samples you take, the closer to normal your distribution comes, the more accurate it is, and the better measures the mean and the standard deviation are. Okay, so now that we've looked at just how to compute probabilities, technically of x bar, we could do less than, greater than, in between, so I'm not going to do a ton of examples with this because the only thing that's really different from chapter 11 is dividing by this root n. Usually the challenging part for people there is just determining if they're starting with that population information and adjusting to predict a sample, which is exactly what we did. So how do you tell? Usually I think, all right, I have population data, I've pulled a sample, but I know nothing about that sample, right? In this, it tells us nothing about the sample. That means that's what I am making predictions about, which is what we did here. Okay, so now that we kind of have an idea of how to do that, I want to try a couple of other different examples. Okay, so I'm going to turn to the next page, which is also part of your notes if you look online. Okay, so here, let's do some extra examples. Okay, and it's going to look a little bit different. So using the same idea, but it does look a little bit different. All right, so let's see. First example, it says the length of individual fish in a pond have an approximate normal distribution with a mean of 37.2 and a standard deviation of 12. A sample of 36 fish is taken. Okay, what is the standard deviation of the sampling distribution of the sample mean for the 36 fish? Okay, so basically, we're adjusting the standard deviation because we have some population, but we've drawn a sample out of this population. So to adjust the standard deviation, if I were to make calculations, I would use sigma over root n. And that's going to be equal to, sigma is 12 over the square root of 36. So really that's going to be 12 over 6, which is 2. Okay, so that would be our adjusted standard deviation. Okay, the next piece of this is different than what we've done before and a little bit, I think anyway, a little bit more difficult to compute. So it's kind of a more thinking type question. But anyway, it says, what standard deviation must x bar have so that 95% of all samples give an x bar, so a sample mean, within 1 inch of the mean. So we're saying, okay, I'm using this population mean to make predictions about my sample mean. Okay, what standard deviation will make x bar, so that 95% of all samples give x bar within 1 inch of the mean. So for this, I'm just going to kind of draw a picture, but we are going to explain using reasoning. Okay, so if I draw a picture of this, I know that my population mean centered at the middle was given as 37.2. Okay, I know that if I'm within 1 inch of the mean, then that would be a 36.2 over here, just subtracting 1, and 38.2 over here, just adding 1. So I know that in between here, I have, or this is like 1 inch, right? So I have 1 inch, 1 inch. Okay, so now we have kind of the thinking part. Okay, what we want to see is what standard deviation must X bar have so that 95% of the sample means are within 1 inch of the mean. So basically, I want this probability right here, this chunk, to be 95%. Well, if you think back to when we first started the calculations in chapter 11, we looked at just the basic bell curve, and remember that 95% corresponds to approximately 2 standard deviations. So basically we're saying, okay, this is 95% in here. I know that to get that, I'd be 2 standard deviations from the mean over here, and then 2 standard deviations away from the mean on the left. So I know that I need 2 standard deviations, 1, 2 in here, and 1, 2, it's not even, okay, in here, to make sure that all of this is 95%. So all of this is 95%. Okay, so if this is 2 whole standard deviations and this is 2 whole standard deviations, I know that I have a distance of 1 here. Well, really I'm looking at a standard deviation of 1/2. Okay, so I know to cover this inch, I need my standard deviation to equal to 1/2. So there, when I do that, I would get 1/2 plus 1/2, and that covers this whole distance of 1 from the population mean. Okay, so basically 95% is included in, we could say, the z-score of 2, right? So we know 2 standard deviations, or a z-score of 2, distance from the mean of 2 over here, and then over here corresponds to 95%. We've talked about that. Now we need to name what standard deviation we need. Well, the standard deviation would have to be 1/2, because this distance is 1, and 1/2 to cover this whole part right here. So kind of different to understand, a little bit funky because it's not totally computational, but that is sort of what's going on with that. Okay, so let's see if I write that out a little bit. Pencil that. Here we go. Okay, I would say we know, so we know we need 36.2 and 38.2 to be within 1 inch of the mean, within 1 inch of the mean. Okay, since we want 95%, since we want 95%, okay, we also need 36.2 and 38.2 to be within 2 standard deviations of the mean. Okay, so that standard deviation must be 1/2. Okay, so 1 standard deviation must be 1/2. Okay. Right, so a little funky because it's all reasoning. I'm not just going through kind of, you know, the same process that I always use. We're just sort of thinking about what's going on with that. Right, so in part C, it says, in this example, we are using a sample to make predictions about a population. We're definitely not doing that because we're given absolutely no information about the sample to start with. So we know that we're not doing that. Next part, using population data to make predictions about what the mean of some sample will be. Well, here, if we think about it, we're given population data, okay, or I guess the mean here, and we would be making predictions about X bar, so this sample mean. So that is what we would be doing in part B. And then the last one, if we wanted to read it, using sample data to make predictions about what the mean of some sample will be. Okay, we're not going to use a sample data to make predictions about the mean. If we had sample data, we would simply just know what the sample mean is because we could find it for that data. So definitely not doing part C either. All right, so that's one kind of different thing we'll see than our usual just typical calculations. Okay, let's do something else that's slightly different as well. So next example says, the gestation time of humans has an approximate normal distribution with a mean of 250 days and a standard deviation of 6 days. A simple random sample of newborns is taken. How large of a sample is needed, and so the sampling distribution of X bar has a standard deviation of 0.5 days. Okay, so notice the big thing here. We're asking how large of a sample size of a sample is needed. Okay, so really when we're doing that, remember our sample, we've just been calling n, our sample size we've been calling n. So really I'm trying to figure out n. So what we want is we want n, our sample size. Okay, and we want this so that the sampling distribution of X bar has a standard deviation of 0.5 days. Okay, so if we had the sampling distribution of X bar, we would be adjusting the standard deviation. And I know that I want to adjust that to be equal to 0.5 days. Okay, so we don't know what our n is. However, we are given that our standard deviation is 6. So I can actually fill in 6 right here. Right. At this point, what I need to do is a little bit of algebra. So I'm going to solve for this. I'm going to multiply the root n to the other side. Doing so, I would get 6 equals 0.5 times root n. Now I'm going to divide the 0.5 over to the other side. So I'd get root n equals, let's see, 6 divided by 0.5 would just be 12. And to solve for n, I just need to square both sides. So I would get n equals 144. There we go. All right, so it looks slightly different. Kind of the same idea as when I guess I don't learn how to do this yet. So if you're finding a sample size, if you're trying to find a sample size, you're essentially just doing a little bit of algebra to solve for n. Okay. Let's see, next example. It says a polling company uses random digit dialing to select the households to be interviewed. In one city, in 1,000 calls, 15% of the calls reach an unlisted number. Okay, this is not surprising since 18% of the residential phones in the city are unlisted. Okay, so we're figuring out what the number 18% is. So here, if we think about 18%, this is not surprising since 18% of the residential phones in the city are unlisted. So the number 18% would be a parameter here. This would be a parameter because we're looking at the entire city and not just that sample of 1,000 calls. So 18% is a parameter because we're looking at the whole city. Okay, here if we wanted to think about a statistic, the statistic in here would be 15%, and that's because it comes from the sample of 1,000 calls. So this 18% is a parameter because we're looking at the entire city, which is what we're considering our population here. So here, the city is the population, the 1,000 calls would be our sample. Okay. Okay, and then finally, last question, sort of a reasoning thing. Which sample size would give me a smaller standard deviation of X bar? Well, remember, when we're finding X bar, so our standard deviation, we're dividing by root n. So when n is bigger, we have a smaller standard deviation. 36 is smaller than 35, therefore it would give us the smaller standard deviation. Okay, so that takes care of a lot of the things that you'll see when you're working in Chapter 13. There will be things that you have to kind of combine from Chapter 11, so you'll still have to have that knowledge, and now we're basically adding this extra piece and saying, okay, if I have this population information and I want to predict a sample mean from it, what happens when I just pull some sample size out of that population? I can use the population mean to make predictions about what the sample mean would be, because we don't know what it would be. But in order to do that, I have to adjust the standard deviation. The central limit theorem is what tells us that we can do that. Right, so in the next video, assuming that I get classroom space for it, I will just go over the proportion part of this chapter, and that will basically take care of kind of each piece of information.